Right. Let's assume that this is your ground level and you have a superstructure which is built on a raft foundation, and the width of this raft foundation is B. So B is the width of your foundation, and this is your planned structure. And then you can see this circle here at the very bottom, and the deepest point in the very bottom of this circle has a distance of 3 times B from the bottom of the foundation. And all this area within this zone, which is confined between the perimeter of this circle and the bottom of the bed of your foundation, is known as zone of influence. It means that the effect of construction on the ground level will impact the stress state only within this zone. Now, this means that if, let's say, if you have a cavity at a depth more than 3 times B, then it means that you really do not have to be worried about that cavity. But if you have anything but this zone, since this zone is all impacted by the stress state change from construction, then this needs to be studied. So 3 times B is the maximum depth of influence, and this is your zone of influence. Now let's assume that before construction, well, you know how tall your building is, so you know how much load is going to apply onto the ground, and based on that, let's say next year you will learn how to design the dimensions and type of your foundation. Let's say that you have decided on B as the width of the foundation, and this is the 3 times B, the depth of zone of influence. Now, within this area, you've got a number of boreholes. From one of these boreholes, you've obtained a soil sample, and this cube is your obtained soil sample. Now, I've magnified this. This is a cylindrical, let's assume that this is a cylindrical soil sample. Let's assume that this is a sample which is taken from the ground by the use of Shelby sampler or U100 sampler, depending on the country that you are practicing. So Shelby is more American, U100 more British. And the diameter of your soil sample is 100 millimeters. That's why this, let's say the mold which you push into the ground is known as U100. And the height really varies. It's a core sample. And you will wrap your soil sample, you send your soil sample to the laboratory. Now, in the laboratory, you need to retrieve a soil specimen from this soil sample. Well, you will retrieve a number of soil specimens from your soil sample to do a number of different types of tests. Today, you're only interested in consolidation tests. So your soil sample is in, your soil specimen will be in a ring. You can see that the end of your ring is quite sharp, so you can push the ring inside your soil sample to get the undisturbed, good quality soil specimen. Now, the diameter of your ring, the internal diameter of your ring, is something between 75 to 50 millimeters, not really between, it's either 75 millimeters or 50 millimeters, depending on your ring type. Both are standardized, and the height of your soil specimen is 20 millimeters. Now, this ring is known as Oedometer ring, and the specimen that you will retrieve from your soil sample is known as Oedometer soil specimen. Now, normally we go for 75 millimeters of diameters, but yes, we do have 50 millimeters of diameters types of soil specimens, Oedometer soil specimens as well. Now, this is obviously not to scale, so you don't have to be worried about the scale. Right, now you can determine a number of soil parameters from your soil for your soil specimen. Let's begin with bulk density. Now, this is your Shelby sampler. It has a certain volume, so you can measure the volume. If it's wax, you can put it in a cylinder full of water and measure how much water is kind of displaced, and that is equivalent to the volume of your soil sample. So you can measure the volume, or you can have a micrometer and directly measure the volume of your U100 sample. And M is the mass of soil sample. Obviously, you need to take off the wax, weight it up, and measure the M. Raw bulk density is M divided by V. V is volume, and since you are dealing with a cylinder, your V volume is equal to A, area of, well, that's the cross-sectional area of your cylinder, multiplied by H, that's the height of your cylinder. So bulk density can be easily determined. Now, if you have the bulk density, then you have the unit weight. Bulk density multiplied by G, gravity acceleration, is unit weight. You can also measure the natural water content. Let's say you can take a small soil specimen from your undisturbed soil sample, put it in the oven, measure the mass of dry soil, that will be M sub S, subtract M sub S from total mass to get the mass of water, and divide mass of water by mass of solids to get your water content, and that's your natural water content. You can also measure the dry density. Now you have the bulk density. Dry density is basically mass of solids divided by total volume. You can either directly measure the dry density or use this very useful phase relationship. Rho sub D, D stands for dry, rho stands for density, is equal to rho divided by 1 plus W, and W is your water content. I remind you that when you are deriving rho sub D from rho using this equation, your W is in form of 0 point something. So if, let's say, your water content is 20%, you will not write 20 for W. You will put here 0.2. And you can also determine the initial void ratio. Now, E is void ratio, and this subscript 0 is here to say, well, this void ratio is the initial or original void ratio. Now, this is another useful phase relationship, which is not really on your formula sheet, but I have brought the proof here. E naught, well, your void ratio in this particular case, your initial void ratio in this particular case, is equal to rho sub S, that's the density of solids, divided by rho sub D, that is the dry density, minus 1. So E equals rho sub S divided by rho sub D minus 1. Let's see why this is valid. Now I'm trying to bring the proof here. Rho sub S is density of solids, so mass of solids divided by volume of solids. Rho sub D is the dry density, so that's mass of solids divided by total volume. Minus 1 equals. So this term is equal to M sub SV divided by Vs M sub S. And M sub S goes with M sub S. So if you simplify this mathematical term, you will get V divided by V sub S. And I have kind of, brought the minus 1 here too. That is equal to V minus V sub S divided by V sub S. And that is equal to V sub V divided by V sub S. Total volume minus volume of solids is volume of voids. Now, by definition, volume of voids divided by volume of solids is void ratio. So this phase relationship is correct. You can memorize it. It's a useful phase relationship. And then rho sub S itself. Now, let's say you need to compute the initial void ratio of your soil sample. You need to have your rho sub S. Rho sub S itself is equal to G sub S, that's the specific gravity, multiplied by rho W. Well, in fact, this is the definition of specific gravity. And rho W is constant on Earth. It's equal to 1 gram over centimeter cube. So rho sub S effectively is equal to G sub S, specific gravity, if your rho sub S is reported in gram over centimeter cube dimension. And G sub S, specific gravity, yes, you can measure it in the laboratory. There's a standard technique, but it varies really between 2.6 to 2.7, 2.75. And for the majority of cases, you can confidently assume that your G sub S specific gravity is around 2.65. Right. Now, we are going to talk about consolidation test, and we know that consolidation test is conducted on fully saturated soils. Soil specimen needs to be fully saturated ahead of consolidation test. It's really the principle behind all classic soil mechanics tests, because what you are studying is really the mechanics of saturated soils. Mechanics of unsaturated soils is a completely different science, and all the equations related to that science are really different with what you are learning now. But mechanics of saturated soils is the conventional mechanics that we use for foundation design. Maybe in future years we kind of find some more courage and move forward to use the mechanics of unsaturated soils. For now, mechanics of saturated soils is what we are studying, and for that reason, all soil mechanics tests, permeability, constant head permeability, falling head permeability, all sort of shear restraint tests that I'll begin teaching in a few weeks' time, and consolidation tests are done on fully saturated soil specimens. Now, it doesn't mean that the soil specimen that you will get from the ground is originally fully saturated. It's not. No, you've got to saturate your soil specimen before testing. So your soil specimen needs to be fully saturated ahead of consolidation test. Depending on soil type, saturation process can take from few hours, let's say if you're testing a sand soil specimen, to 1 week or few weeks, depending on plasticity of your soil sample, and that's in the case of clays. Let's say if you have sand, few hours; if you have clay, really 1 week. If it's a highly plastic clay like London clay, Oxford clay, then probably you will need more than 1 week. But after saturation, your degree of saturation goes up to 1 or 100%. So S sub R, which is your degree of saturation, goes up to 1, that is 100%. And you probably remember this phase relationship. This is, in fact, the first phase relationship that I've brought in your formula sheet. S sub R, degree of saturation, is equal to W, that is water content, multiplied by GS, that is the specific gravity, divided by E, void ratio. Now, in this case, really for all soil mechanics tests, your S sub R at the beginning of the test is 1, fully saturated. So you can say that 1 is equal to W G sub S divided by E. Now, it's at the beginning of the test, so your E is E sub naught, your E is the initial void ratio, and your W water content is in fact W subscript SAT, or saturated. Your water content is the saturated water content of the soil. If you rearrange this equation to bring W sat to the subject, then you can really determine the saturated water content of the soil. That is the maximum possible water content that your soil sample can adopt. W sat is equal to E naught divided by G sub S. I remind you that you already have the E naught, or initial void ratio, from the previous step. G sub S is either you measure it or you assume it. If you assume it, then 2.65 is fair enough. And you can determine your W sat, that's the saturated water content of the soil. So at the beginning of your consolidation test, now I've not even began talking about consolidation, it is all about reporting. On top of your report, you can report the rho and gamma, that's the bulk density and bulk unit weight of your soil. E sub naught, that's the initial void ratio of your soil. G sub S, that is the specific gravity of your soil. You either measure it or assume it. In this case, 2.65 assumed, and W SAT or W sub SAT, that's the saturated water content of the soil, which can also be reported. That's the initial water content that you begin your soil ahead of any form of testing, permeability testing, hydraulic tests, mechanical tests, any form of test, because you're studying mechanics of saturated soils. Right. So let's have a look to our consolidation test. You remember from the lecture that you have a ring. Your ring is around 75 or 50 millimeters in diameters and has a height of 20 millimeters. That is 20 millimeters in diameter. Your ring contains your soil sample. Your soil sample can be disturbed, but normally we go for undisturbed soil samples. That's our preference. You can see these red lines. The red lines are represent, by the way, this is a cross-sectional diagram. The red lines represent filter paper. Now you use these filter papers, which are essentially papers, to make sure that when water is moving in and moving out of the soil specimen, the fines, the clay and silts, small particles are not migrating out or in. So it's kind of, as the name suggests, filter. And you can see that you've got this filter in between your soil and something which kind of looks like bubbles in blue. And these are your porous discs. The porous disc is a metal disc or a stone disc, which is, as the name suggests, porous, and it conveys air and water. Now from bottom, your porous disc is sitting in a chamber, the blue chamber, that's your water bath. Your water bath will be filled with water at all times. And from top, your porous disc underlies a metal cap, which is basically your loading cap. You may have a ball to make sure that the load that applies to the soil specimen is definitely central, or you may not. And there are different loading, if you like, frames, but the traditional loading frame has a rod on top, and this rod is continues with kind of a horizontal lever, which is connected to a hanger. And on this hanger, you can put different weights, different values of dead weight. And by applying this, putting these dead weights on the hanger, the dead weight will be multiplied by a number, which depends on the length of your lever and applies kind of axially and vertically to your soil sample. And that is force, vertical force. If you divide your vertical force by the cross-sectional area of this circle, diameter square pi divided by 4, you can convert that force to pressure. Also, your loading cap is connected to either a digital or a mechanical gauge, and that gauge shows the degree to which the cap goes up or goes down during the course of test. So it can measure the heaving or swelling or settlement subsidence or even collapse. This is really the general layout of your oedometer test, or one-dimensional oedometer test, one-dimensional consolidation test. Your test is one-dimensional because the soil is confined in a rigid ring. It means that the soil cannot show any form of displacement laterally. The only displacement that it can experience is axially. Right, so let's move on. At the beginning of the test, your stress, your pressure, or the pressure which is applied to the soil sample, obviously is 0. It's not really 0 because you have the self-weight of the cap, and normally you put a very small amount of load on the hanger to generate a very, very small stress on the soil sample, just to make sure that all these connections are secure and they are working, and that small pressure which is something around 2 to 5 kPa, is known as seating pressure. But let's say 0 kPa. It's not really zero practically. I've got to put something here just to make sure that all these connections are working. And at the beginning of the test, so time 0, the specimen height is 20 millimeters. Well, that's the standard height of a oedometer test specimen. And delta H, which is the change in the height, or the reading from the dial gauge, obviously 0 because, well, there's no pressure on the soil system. And delta E, which is the change in void ratio from the initial void ratio, which is E0, is also equal to 0 because no stress has yet applied to the soil specimen. Look at this golden equation. You probably may like to memorize this golden equation because you will use it on a daily basis as a design engineer. The delta H divided by H0 or H0 is equal to delta E divided by 1 plus E0. What this equation is telling me. Delta H is settlement or heave, volumetric change along the axial vertical axis, delta H. Basically the reading of this delta gauge, it is this dial gauge or the actual settlement in the field. Divided by H0. H0 is, well, the initial height or the initial height of your test specimen. Or in the field, H0 means, well, the initial thickness of your clay layer. So delta H divided by H0, different definitions depending on what you're doing. Is it about field? Is it about lab? Is equal to delta E, the change in void ratio, divided by 1 plus E0. E0 is the initial void ratio of your soil, and delta E is in the change in void ratio. So at the beginning of the test, well, the stress on your soil sample is 0, the dial gauge is showing 0, everything is 0, and the specimen height is the original height, 20 millimeters. Then you add your first, let's say, dead weight on the hanger to apply the first stage of loading on your soil specimen. And you will keep the soil specimen under that amount of initial load for 24 hours. The stress is increased from 0 kPa, initial state, to 25 kPa. So you have got to apply enough dead weight here on the hanger to generate this 25 kPa on your soil specimen. Now, after 24 hours, under 25 kPa, the specimen height goes down from 20 millimeters. This is strictly speaking an example. It can be anything really, but this is the example. Goes down from 20 millimeters, let's assume, to 19.806 millimeters. It means that the dial gauge reading is 0.194 millimeters. The specimen has settled or subsided after 24 hours for 0.194 millimeters. Obviously 20 minus 0.194 equals 19.806. That's how we got 19.806. That's how you measure the specimen height under 25 kPa worth of pressure. I remind you that at all times, your soil specimen is kept fully saturated. You can see that the water bath at all times is full of water. And yeah. So you've got some consolidation settlement, and what you will measure using this dial gauge is delta H. And from delta H, you can measure the secondary height of the test specimen. Also, you can measure the change in void ratio. Look at this equation, the golden equation. Delta H is, well, subsidence divided by H0, initial height of the test specimen, in your case 20 millimeters, equals to delta E, question mark, unknown, divided by 1 plus E0. Well, you remember that we know how to measure the E0 from all the equations that I presented earlier. Let's look into these equations. Right, let's look into this equation. E naught, this is the equation that I showed in the previous slide. E naught is equal to rho sub s, that's the density of solids, divided by rho sub d minus 1. Okay? Well, rho sub s is effectively equal to gs. It can be 2.65. Rho sub d, you know how to determine rho sub d. That's the dry density of the soil. So you can easily get your E naught or initial void ratio. That's one way. Now let me tell you that there is a second way, probably a bit easier. We know that your soil sample is fully saturated. That's the assumption behind all sort of soil mechanics tests. So your soil sample is fully saturated, and well, yeah, you can measure the water content. That's the saturated water content. We discussed that in the previous slide, so you can have your saturated water content. That's established. Right. Now, since you have your saturated water content, you can make use of another useful phase relationship, which is S sub R, degree of saturation, is equal to WGS divided by E. It's the first phase relationship in your formula sheet. S sub R in this case is 1, your void ratio, your degree of saturation is 1, your soil is fully saturated. W is effective W sat, G sub S divided by E naught. Now, the water content, which is the saturated water content, well, effectively is known. You can have two oedometer samples, identical oedometer samples, keep one for the testing, and put one in the oven to measure its water content, and that water content is equal to W sat. So if you have your W sat and S sub R and G sub S, well, you can determine your E naught or initial void ratio. It's the other way around. If you decided to go through this way, then your E naught will be equal to water content, which you can measure in the laboratory, multiplied by G sub S. So either this way or this way, you can get your void ratio. Really, the choice of approach is up to you. And that is your initial void ratio. So you have your initial void ratio, and you can determine your delta E or the change in void ratio. I'll put an asterisk here. Let's see how and where I've got this 0.16. Okay, so delta H in the first step of loading is 0.194, divided by H naught, which is initial height of the test specimen, 20 millimeters, is equal to delta E. Well, that's the change in void ratio, E naught minus E. This is really E naught minus E because, well, it should be a positive number, and we know that the initial void ratio is bigger than the secondary void ratio. You're talking about consolidation, you're talking about the decreasing void ratio. So that's why delta E is kind of translated into E naught minus E, divided by 1 plus E naught, 1 plus E naught. Now E naught is known. Let's assume that your E naught is 0.648. So if your E naught is 0.648, then 1 plus E naught is 1.648, and E naught minus E is 0.648 minus E. Everything known, with an exception of E, you can determine the E. E is your secondary void ratio, and that is equal to 0. Right, E is, you can determine your E, your secondary void ratio, but here what I have put is 0.648 minus E, which is delta E, and that is equal to 0.16, and I've brought it here. You can also determine the E or the initial or the secondary void ratio at the end of first phase of loading. So this first phase of loading takes 24 hours. When it's finished, you can top up the load. How? By doubling up the dead weights. And you go up from 25 kPa to 50 kPa. Again, you will keep your soil specimen under 50 kPa for another 24 hours. Then you will measure the delta H, the change in height, during the second step of loading. Now in this example, that was 0.073, and well, you have the kind of initial height of the test specimen. You know that the height is gone down for 0.073 millimeters, and this will be the secondary height of the soil specimen at the end of 24 hours under 50 kPa. And you can determine the delta E again. Same, this will take 24 hours. You go to the second set, doubling up the load from 50 kPa to 100 kPa and redo the test, repeat the test. And in fact, you can do this as many times as you need. So look at here, I have then gone up from 100 kPa to 200 kPa, 24 hours, 400 kPa, 24 hours, 800 kPa, 24 hours, and I've registered all the delta H values, which are measured by using a digital dial gauge, LVDT, or a mechanical dial gauge. And this is really the raw test results which comes from a oedometer test. So I'd like you to look into the raw results here again. I have a number of loading steps. So in this example, 6 loading steps. In the first loading step, the initial effective stress was 0, then it was topped up to 25 kPa, kept under 25 kPa for 24 hours. At the beginning of the test, the height of the test specimen was 20 millimeters, and then it gone down to 19.806, and that was because of 0.194 millimeters of settlement or subsidence, which was measured by the dial gauge. The initial void ratio of the soil specimen was 0.648, and the secondary void ratio of the soil specimen was measured as of 0.634. This is 0.648 minus 0.648 minus 0.016 equals 0.632. So that's your secondary void ratio. And you can do the very same analysis for step 2, 3, 4, 5, and 6 to measure the secondary void ratio, which is the void ratio at the end of each loading step. That is 24 hours. So look at this. What you have here effectively is sigma dash, the stress, that sigma dash 2 effectively, the stress which is applied to the soil specimen, and E2, the void ratio that the soil adopts at the end of 24 hours under these values of stresses. So you have a data set, effective stress versus void ratio, and this can be plotted like this. So you have void ratio. In this case, I've not put the void ratio. I've simply speaking put the delta H or deformation, the very value that I read from the dial gauge, multiplied by right. So sorry, this is not the diagram I was going to show you. This is the diagram. So I correct myself. So you have a data set. You have sigma dash, effective stress, versus E void ratio. Look at this. Void ratio on the vertical axis and sigma dash on the horizontal axis. And you can see that I have a number of data points all here. Now, I remind you that these void ratios are void ratio at the end of each step of loading, and sigma dash is effectively sigma dash 2. So you have a number of, let's say, data points, and you can connect these data points to one another, or you can draw the best fit curve, and that will be your E versus log sigma dash diagram. Now, it's customary to use log sigma dash instead of sigma dash to get as straight as possible lines in this diagram. Now, you remember the Terzaghi's method, which we use to determine sigma dash C, or pre-consolidation pressure. So you will find the point of maximum curvature in E log sigma dash V curve, and you draw a horizontal line. Then you will draw a second line, which is tangent to the point of maximum curvature. And then you will draw the bisector, between the horizontal line and the tangent line, and that is your dashed line, the bisector. And then finally, you probably can see this green line. The green line is the line which is tangent to the normal consolidated or virgin part of your E log sigma dash V curve. Now, this green line intersects the dashed line, the bisector line, in a point. If you read off the sigma dash which corresponds to this intersection, your sigma dash will be equal to sigma dash C, or pre-consolidation pressure. Pre-consolidation pressure is the maximum pressure that the soil has ever experienced in its lifetime. Now, your diagram has two parts. It has a part which shows a very little change in void ratio with increasing effective stress. So it kind of tells you that the soil in this stage is pretty much strong. Over-consolidated line, if you remember. And then you have a part which will kind of tells you that small amounts of variation in effective stress will cause tremendous amounts of void ratio loss. This is the normally consolidated or virgin line, or the normally consolidated state of soil, which kind of tells you that the state of soil here is pretty much weak. Now, the slope of over-consolidated line is known as C sub S, or swelling index, and the slope of normally consolidated line or virgin line is known as C sub C, or compression index. Compression index and swelling index, together with pre-consolidation pressure, are intrinsic parameters of the soil. It means that these are like ID cards of the soil. They will never change. So for any soil sample that you get from a certain depth, from a certain location, you will have one single C sub S, C sub C, sigma dash C forever. And that's kind of the intrinsic parameters of the soil. Right. Now, this is the diagram. The blue diagram that I showed is the diagram which pretty much is the outcome of a oedometer test. And to build this diagram, well, you need to spend so many days. You need to spend probably 1 week to get your soil fully saturated, and then to build each of these data points, you need to spend 24 hours. So this is pretty much valuable. Now, I'd like you to look into each of these loading steps. Each of these loading steps. For each of these loading steps, the soil is kept under load, is kept under pressure for 24 hours. And yes, I can see this delta H, which is let's say the final settlement of the soil after 24 hours. But in fact, you can measure the variation or evolution of delta H with time. And if you do that, you can get this diagram. that I presented initially by mistake, this diagram. So on the vertical axis, you have deformation, delta H in millimeters. And on the horizontal axis, you've got time. So for this test, you've got 6 loading steps. So you will have 6 of these diagrams. Look at this. The red curve is showing the variation of deformation with time. You can see that initially, after loading, in the first few minutes, first few hours, in fact, the settlement, the subsidence is pretty quick. And then as the time goes, the settlement, the deformation gets slower, and adopts kind of a slower rate. So let me remind you that the vertical axis is delta H deformation, and the horizontal axis is t time. Now, you can have this diagram in so many ways. What I recommend you to use is deformation versus root time. So instead of time, I like you to use root square time. That is root square time. As I said, there are so many different ways of presenting the data, but the root square time is the technique that I recommend. So you've got this red line, this red curve. This red curve is showing the variation of deformation with root square time. And you can get a parameter from this diagram. That parameter it can be reported for each and any of these loading steps. Let's see what parameter I can get, and then in a few weeks' time I will tell you why this parameter is pretty important and where we can use this parameter in our analysis. So look into this red curve. The red curve has a point of maximum curvature. You'll find the point of maximum curvature and you will plot a tangent line. Your tangent line, which passes through the point of maximum curvature and obviously is tangent to your curve, will cross-cut the vertical axis at a point and the horizontal axis at a point. Now, for the horizontal axis, I'm going to call the intersection point A, and the origin is O. Now, OA is a line. You can have a roller, a simple roller, and measure the distance between O and A and report it. Whatever that distance is, you need to multiply that distance by 1.15 to get a second point on the horizontal axis, and that second point is B. Now, OB, which is a line, is equal to OA multiplied by 1.15. Why 1.15? It's an empirical number, and it's a convention. Let's put it that way. It's a convention. So you found a second point on the horizontal axis. If you now connect this second point on the horizontal axis with the point of intersection on the vertical axis with this dashed line, okay, your dashed line will intersect your curve, your data curve, in 2 points. Forget about the first point, look into the second point. The second point has a time which corresponds with it, and that time is known as T sub 90. Now, since your horizontal axis is in root time, that time is also in kind of root square, T sub 90. What does T sub 90 means? T sub 90, T is time. T sub 90 is the time needed for 90% of the full amount of consolidation to take place. So simples, T sub 90 is the time needed for 90% of full consolidation under that certain load, whatever your loading step is, to take place. It is reported in minutes, and it's a pretty important parameter. I'd like to look into this. So we have loading steps 1 to 6. For each loading step, I have the initial effective stress, the secondary effective stress, the void ratio at the beginning of that loading stage, and the void ratio at the end of that loading stage. Now I have root square T sub 90, which can give me T sub 90 in minutes. As I said, T sub 90 is a pretty much important parameter. You can get a number of different parameters from T sub 90. The first parameter is something known as C sub V, coefficient of consolidation. Now I'd like you to look into the dimensions of coefficient of consolidation. You have centimeters square over hour. So you have time and you have distance. Can you guess what this parameter, coefficient of consolidation, is useful for? It has time and it has distance. Can you guess what sort of assessment, analysis, this coefficient of consolidation is useful for? It has time and it has distance. Remind you that consolidation is all about the settlement of the foundation during a long period of time. I think you have guessed that this parameter, C sub V, or coefficient of consolidation, is useful to determine the time needed for any proportion of the full picture of consolidation to take place. Let's say if you calculate the full consolidation settlement as of, I don't know, 20 centimeters beneath the foundation. That 20 centimeters, depending on the depth of your clay and the load on top of the clay, can take, I don't know, 10 years. You might be interested to know how much of that 20 centimeters of settlement can take place in the first year, by the end of second year, by the end of third year. This is your parameter, C sub V, coefficient of consolidation. Now, how you can determine that, it's a different story. I will talk about this. But first, we are looking into parameters that we can get from a simple oedometer test. Now, how can you get this very, very valuable parameter, C sub V? Now, you can determine your C sub V by using T sub 90, which is a reference time needed for 90% of consolidation to take place. I'd like you to look into this equation. C sub V is coefficient of consolidation. C sub V is coefficient of consolidation. C sub V is in centimeters square over hour. This is equal to, in this equation, your C sub V should be equal to centimeters square over hour. Dimensions are very, very important. If your C sub V is in centimeters square over hour, then your C sub V will be equal to a constant, which is 0.848, multiplied by H sub dr. This is the drainage length. I will tell you what this drainage height or drainage length is. H dr square, this must be in centimeters, divided by T sub 90. Your T sub 90 should be in hours. So remember, your T sub 90 that you determine from our oedometer test is normally in minutes. So you've got to convert minutes to hours. This is very important. And all your heights in oedometer test are in millimeters. You've got to convert those in centimeters to make use of this equation. What is HDR? Well, this is a constant, and T sub 90, I know already how to determine T sub 90, but so let's look into HDR. HDR is the drainage length. This is your test specimen, or let's say the cross-sectional diagram of your test specimen. It has a height at any stage of consolidation, and it is confined between two porous discs. H sub dr is the maximum distance that a droplet of water should travel in order to get out of the soil system, because consolidation is all about migration of water out of the soil system. If your soil sample is confined between two porous discs or two drain points, then your HDR is always equal to half the height, whatever the height is. So HDR at all times for an oedometer test is equal to half the height, because in an oedometer test you've got two drain points, one at the top and one at the bottom. So you can see that C sub V can be easily determined directly from a one-dimensional oedometer test, and it can be reported here. C sub V in centimeter square over hour something. You can see that for each loading step, you've got a certain value of C sub V. The next important parameter that you can determine from an oedometer test is M sub V. This is coefficient of volume compressibility. Now, C sub V is useful for time analysis. M sub V is useful for determining the degree of settlement, basically the total settlement of your foundation. So it is a very important parameter, M sub V, coefficient of volume compressibility. Let's see how we can determine coefficient of volume compressibility for each loading steps. Look at this very simple equation. M sub V, coefficient of volume compressibility, is equal to delta H, how much the dial gauge is showing you. At each loading step, how much the dial gauge is showing you the displacement, the dial gauge reading, delta H, divided by H1, the initial height of the test specimen at the beginning of that loading step, whatever that loading step is, multiplied by 1, divided by sigma dash 2, effective stress, 2 minus sigma dash 1, effective stress 1. Sigma dash 2 is your topped up stress, and sigma dash 1 is the initial effective stress. So let's say for step 4. For step 4, the soil specimen at the beginning of step 4 loading is under 100 kPa. And then you will top up the load on the hanger to get the load, get the pressure up from 100 kPa to 200 kPa. So 200 minus 100, 100. The initial height of the test specimen is H1. H1 is the initial height of the test specimen at the beginning of stage 4. Stage 4, so let's look into stage 4. This is stage 4. There we go. H1 is here, 19.60. So at the beginning of the loading step, the height of the test specimen was 19.6. That's H1. And delta H, how much the dial gauge showed you in terms of displacement at the end of that loading stage. Loading stage is 4, delta H 0.243. So M sub V for M sub V for stage 4 is delta H 0.243 millimeters divided by H1 19.6 millimeters multiplied by 1 over sigma dash 2 200 kPa minus sigma dash 1 100 kPa. And your dimension here is millimeters goes with millimeters, so your dimension, your unit is, well, 1 over kPa. Now, how M sub v is useful. Let's see how M sub v as a parameter is useful to us. I'd like you to look into this equation now. Delta H here is the consolidation settlement in the field. Delta H here is your consolidation settlement in the field. Consolidation settlement is equal to H, the thickness of your clay layer, multiplied by M sub V, which is a number, in 1 over kPa, multiplied by delta sigma. This is the effect of surcharging, or let's say the change in stress state because of construction, superstructure rate. As simple as this. This very simple equation can give you the exact amount of consolidation settlement in your clay layer, clay strata. So M sub V is quite useful in this sense. There is one other useful parameter that you can determine for each loading step, and that is K. Do you remember K? K is permeability, coefficient of permeability. Probably you remember when I was teaching the permeability lecture, I taught you the constant head per millimeter, and I said that constant head per millimeter is a device that we use to measure the permeability of coarse-grained soils. These are large-grained soils, these are sands and gravels. And I told you that, yes, you can use the same facility, the same apparatus to measure the coefficient of permeability of fine-grained soils like silts and clays, but that takes a tremendous amount of time. You have two ways to go around this problem. One, to do another test which is known as falling head test, and I taught that in my tutorial. But I said I normally do not choose to do the falling head test. I instead choose to do the oedometer test, because oedometer test can help you to let's say, calculate the amount of consolidation settlement beneath foundations and the time which takes the full amount or a proportion of that consolidation settlement to happen. And at the same time, it can help me to measure the permeability of the soil. So, well, you can see how useful a oedometer test is. K is permeability. Let's see how we can determine the permeability from a simple oedometer test. I'd like you to look into this equation. C sub V is coefficient of consolidation. We can measure C sub V, coefficient of consolidation, for each loading step. M sub V is coefficient of volume compressibility. We can measure the coefficient of volume compressibility for each loading step. Gamma W is unit weight of water. It's constant, always 10 kilonewton over meter cube on Earth. And K on top is your permeability. Depending on the units that you're using here, you can control the dimensions or units of permeability. So you can see that you can measure the permeability of your clay soil at the same time as you are measuring the consolidation parameters for your soil specimen. So pretty much useful. Now let me ask you a question. Well, this seems to be a very useful equation to measure the consolidation settlement beneath foundations. Consolidation settlement beneath the foundation is equal to H, that is thickness of your clay soil, which is fully saturated, or you assume it to be fully saturated beneath the foundation, multiplied by delta sigma, will be the surcharge or the effect of surcharge on your clay soil, multiplied by M sub V. It seems a very, very simple equation. But let me ask you a question. Well, you've taken a soil sample from a depth and you've done a oedometer test. Now for each loading step, you've got an M sub V value. Which of these M sub V's are you going to use to determine the total consolidation settlement beneath the future foundations. You have taken your soil sample, you have done a number of loading steps. For each loading steps, you have measured a value of M sub V, coefficient of volume compressibility. Which of these M sub V's you need to use in your settlement analysis? Some of you may say, well, average. Some of you may say, oh no, not the average, maximum M sub V, because I'm quite cautious. And I will tell you that both of you guys, both of these responses are wrong. Not the maximum, not the minimum, not the average. Your M sub V should be accurate. So which of these M sub V's for these loading steps you need to use in your analysis? It shouldn't be minimum, shouldn't be maximum, shouldn't be average. Right. So let's have a look. So this is your ground level, and let's say your ground level is here, and let's say the groundwater level is standing on ground level. This is GWL, groundwater level. And let's say you are interested in this point. Let's say this point is in the middle of your clay layer. So let's say you have a clay layer, and you have chosen the middle of your clay layer to calculate the consolidation parameters. And it's in the middle, so it kind of represents the entire layer. You've got a layer of clay, you have chosen the middle, and you are determining all these consolidation parameters for the middle. Now, your Z is the distance between your soil sample and the ground level. And you know that the unit weight of soil is gamma. So you know that the vertical stress or total vertical stress before construction is sigma naught, that is equal to gamma times Z, simples. You also know that, well, since the groundwater level is standing on ground level, your pore water pressure or pressure of water is equal to gamma W times Z. Z is equal to ZW. This is the height of column of water standing on your point of interest. So your UW is gamma WZ. And you can use the principle of effective stress and calculate your effective stress, your initial effective stress. That's sigma dash naught. That is equal to gamma minus gamma Z multiplied by Z, or sigma minus UW. Okay, this is your initial effective stress. You're planning to build a two-story building. That is your superstructure, and this is your point of interest in the middle of the clay layer. And you know that after completion of building, your final effective stress will be equal to the original effective stress plus, let's be very conservative, plus the 100% of the weight of the superstructure. Simples. Okay, so I know that for this specific point, in terms of a stress state change, I'm moving from a certain sigma dash naught to a certain sigma dash F naught. Let's say, for the sake of argument, I'm moving from, let's say, 250 kPa to 350 kPa. I know that. 250 kPa to 350 kPa. Let's assume it, okay? 250 to 350. Okay, let's see. So I'm moving from 250 to 350. So I'm in this range. This is the range valid for 200 to 400. I'm moving from 250 to 350. So my loading step 5 kind of matches what I'm looking for. So if I can determine the M sub V for loading step 5, this M sub B value can be used in determining my consolidation settlement. Same business for C sub B. If for some reason you are interested to know, well, how much of this total settlement is going to happen in, I don't know, 10 years time, 2 years time, then you have got to use the C sub for load step 5. So it's very important to understand what is happening in the field and get the relevant data from the laboratory testing to match that actual happening in the field.